Hi. At the day job, I'm swamped in what we name external calls. They have nothing in common with what I'm about to show here. But they made me think of these, so that's our theme for today. Here, I'm setting up a beginning point in the C language. A clean program easy to compile in one simple line in the terminal. Hello world. Okay, this works. Now, for something a bit more complicated. The inverse square root of 2. It's also easy to compile and gives a correct result. But how long does it take? Let me quickly add code to measure that. Still nothing complicated to compile and a correct result. Wonderful. Let's move on to another function. That's the fast inverse square root function from the Quake source code. I just copied it over from Wikipedia. Again, all is contained in this source file. Therefore, the compilation is easy. But now, we are about to get into the heat of it. Our first call to an external language. The modification of the C program is easy. Just don't forget that with GCC and gfortran, the argument is passed as a pointer. Of course, we need some code in Fortran. Here, for the compilation, first we compile the Fortran code into an object. Then we compile the C code and link against the Fortran object. This is possible because basically the both compilers make a set of binary instruction. The linker just has to connect the correct addresses in program space. And the language in which the code was written doesn't matter anymore. And that's how you do external calls in C. Let's keep on the fun work. Fortran is incredibly efficient for maths, but assembly is where the fun's in. Again, I start by modifying the base C code to accept external functions. Then I do some reading and understand I will try 2 functions. This is because I discovered there is an assembly instruction that directly gives the inverse square root. So for the slow function, I compute the square root and store it in the XMM1 register. Then I load the number 1 in memory. I divide 1 by the square root result and store the result in the XMM0 register, that's the argument register. When you make an external call from C with a float argument, the argument will be in XMM0. Then I just need to define the number 1 in memory. And here is the 1 instruction inverse square root code. We can have both functions in the same object file. The linker will connect the functions to the correct places in the C executable. So here are the 2 stages of compilation and the correct result. I took some time to rewrite the Quake inverse square root function in assembly. I will not talk about it in this video. Here we talk about external calls. How to code it in assembly is a conceptually different matter. Suffice to say, I ended up with a clean and a hacky function. While I'm at it, I think I will code this operation in Python also. I'm told you can compile Python scripts and link them against C programs. And likewise, you can expose C functions to Python programs. I believe that's how NumPy works. But I never needed to learn how to do that. So I'll leave it to you as an exercise. Anyways, that was with the base Python math library. Now for the NumPy analog. NumPy is great in that it can work in a parallel manner on arrays. That's called vectorization. So here are 1 million square roots on a size 1 array. And 1 million square roots at a time on a million-sized array. So far, so good. Let's put all of that into a bash script and compare the program results. I don't like bash, I find it complicated. So what can we say so far? So the basic C function needs 20 nanoseconds. The fast Quake function is actually slower. That's the result of 30 years of improvements on CPU. The compiled basic C function likely employs material instructions better than the complex Quake function. Fortran, hyper-optimized for maths, is slightly faster. No surprise here. I'm actually pleased by my assembly code performance. The fastest is of course the 1 instruction routine. But the assembly Quake holds its ground well. Python is slower. up to several milliseconds. So why would anyone write code for Python? Well, the answer is in the last test. 3 milliseconds for a million square roots computed in parallel. That's 3 nanoseconds per square root. All because we silently made an external call to well-written NumPy code in C. And without the C complexity. But this benchmarking is actually completely nonsensical. Because in order to uncode, the OS has to do a lot of things. Memory allocation and so on. So let's simplify our codes and make a bash script to run the resulting program several times. Oh, I forgot to echo the mean. All corrected now. That went well, so here is a zen moment of me updating the other programs at 1000 speed. When I had 2 functions in assembly or Python, I made 2 programs. And compiling now. Oh dear me. I cut the printf out of the clean assembly function. Back to bash scripting to test all that. Perfect. If you followed along the Python script simplification, then you have noticed I have made several mistakes in deleting my variables. But they are all corrected now. I can make a more complicated bash script. Run all programs, and echo their results. And I just have to change the number of repetitions to have a better averaging. Say 1000. It would be more honest to have 1 million, but that'll take time and I want to play video games. So 1000 it is. And here are the final results. If I read the nanoseconds well, it's about 1.7 millisecond in each case. So why bother with low-level languages when Python seems to be as fast? Well, because external calls allow to write simply a function. And both the Quake assembly and the NumPy vectorized script demonstrate the effect of well-written efficient code. Managing high and low-level code is a matter of writing one very efficient code and reusing it in abstract situations. And that's it. This is the end. Thanks for watching. See you next time. Or stay for a message from the sponsor of this video. Me. I'm the sponsor of this video. It has once been said, we must be very careful when we give advice to younger people. Sometimes they follow it. I'd argue we should be even more careful when teaching them low-level programming languages. Because sometimes even 20 years later, they do it again for fun. I know.